constant acceleration is free fall. Okay, and free fall is defined as an object moving under just gravity. And I'll explain what that means in a second. But here's sort of like if you take a bunch of pictures, we could actually. I'm thinking about doing this as a lab. If you just set your camera to take a bunch of pictures at a particular frequency, like every second, and then you overlay them on top of each other, which is a pretty easy image processing thing to do. You can actually see like the motion. And what do you know when the balls are closer together? What's happening there? Are they moving faster or slower? Slower. And when they're farther apart, they're moving faster. So these pictures are all taken at the same time interval. And so essentially what we mean by free fall is it can't be touching anything. Okay? It can't be touching anything at all. So for instance, if I'm holding this Post-it note, is it in free fall?
No.
Okay. When I drop it, it's in free fall from the very moment it leaves the contact with my hand right up until it hits the ground. Okay? What if I throw it in the air? When is it in free fall? The whole time it's not in contact with my hand. So as soon as I let go of it, right, and right before it lands on my hand, that's free fall. As soon as it contacts something else, not free fall. And that's because as it sits on my hand, right, it still has the force of gravity acting on it, but what else is acting on it? The force of my hand. So I'm pushing up, which is called a normal force, and gravity is pushing down, so the net force on this thing is 0. If I'm throwing it, right, I'm pushing force on it to give it an acceleration, so I'm going against gravity and doing work on it. We'll talk about that later. So those forces aren't, there's an acceleration, but it's not gravity, right? It's the acceleration I've given it. And then once it leaves my hand, the only force acting on it is gravity, and therefore the only acceleration is the acceleration due to gravity. And because that's down and I threw it up, right, it's got a velocity going up, an acceleration going down, so it slows down, comes to a stop, and then comes down and speeds up, okay, in a very nice symmetrical way. So what's crazy about this is while it's going up, if it's right here, at the going up part and at the going down part, it should be going the same speed because of this nice symmetric parabola thing, because the acceleration is constant. So even though the directions are reversed, if you're at 2 points in the same arc that are at the same height, you should be going the same speed. So just a fun fact. Okay, so free fall is an object moving under the influence of gravity only, okay? And if we do our little snapshot graph and we draw our velocity vectors, it looks something like this, but the velocity is constant. Oh, Lori Beth, do you have a question? I don't know if I can hear you. Can you type it in the chat? For some reason I can't hear. I'm a speaker. Select a speaker. Okay, do you have a question? I think I can hear you now.
It doesn't look like it's being recorded from our end.
Oh, cool. All right.
Recording in progress.
Now it's being recorded. Okay, thank you. So,
Will you redo those other constants since they didn't get recorded?
they record. I record it twice because sometimes I forget to record one of them. So it's still being recorded, just not on the cloud.
Okay.
I've already made this mistake once, so I made a checklist, and I somehow didn't get it right still. There's a lot of things on this checklist. There's 11 things I have to do just to start class, so that's too many. I'm going to have to make a better checklist with, like, some sort of physical thing that I have to check. Okay, good thing I'm not doing rocket launches. So we have a constant acceleration, and we can plot this. And why does it look like this? What's the slope going to be? Negative, right? So here's our velocity versus time graph. What do you think the slope of this graph is? It turns out it's negative 9.8 meters per second squared. So g is 9.8 meters per second squared. You always have to include the negative. It's not included in the letter g, right? This is a constant, right? It's the acceleration due to gravity, but it has some limits to it. So there are universal constants, and then there are just like constants. This is not a universal constant. Universal constant means it's true everywhere in the universe. But gravity, this acceleration due to gravity, not true everywhere in the universe. It's related to the gravitational constant, but not totally the same thing, okay? So little g just means 9.8, and that's pretty much the acceleration due to gravity around sea level. So any two objects in free fall, regardless of their mass, and this is a very important point, have the same acceleration, okay? So if you have a dropped ball, let me just show you what the different graphs look like, okay? So if you drop a ball, this is what it looks like. It's falling, right? That's its position in y with respect to time. This is its velocity. This is its acceleration. You'll see it's negative 9.8 because we've kept all the directions the same. What if we toss a ball up? Well, we're going to start from 0 now. And this looks something like this. You'll notice it starts higher than it ends up. So we start at this non-zero thing. It goes up and then down. You can see the same slope, right? This is the same slope, but what does it do this time? It crosses 0 because there's a point at which it turns around, okay? The other one didn't cross 0 because it started at 0 and only went down, but we still have the same acceleration, okay? So whenever you have free fall, your acceleration graph should look like this. All right? Okay, here's a question. I'll start the timer. Okay, I'm mostly thinking B or C. Please discuss, we'll vote again. Ooh, okay, yes. So remember, does this depend on mass? No, okay. With air resistance, then we have to worry about shape, but free fall never depends on mass, okay? All right, so we're gonna watch this, and then this will be pretty much the end of where we're at. But in case you don't believe me, although all of you picked C, there's a lovely clip from this BBC show that shows an actual giant vacuum where they drop a bowling ball and a feather, and it includes Brian Cox, who's like some sort of British Neil deGrasse Tyson, and also does a pretty good, he comes on tour through San Diego periodically and does like a pretty good show with, he has like a podcast with his friend who's a comedian. Anyway, he's not particularly funny, but he is very British. To recap, one, why did they fall at the same rate? The only force on them is gravity. Their only acceleration is the acceleration due to gravity, and it does not depend on the mass, okay? Why do they fall at different rates when there's air in the room? Yeah, they're interacting with the air, right? So that means it's not technically completely in free fall because there's air resistance, which is a secondary force, okay? Also, it's kind of so I used to show a video that, this is a more recent one, there was an experiment, like the first moon landing, one of the scientific experiments they did on the moon landing was they just took like a hammer and a feather and they dropped them because there's significantly less air on the moon because you have to bring your own. And so you can basically do that experiment without pumping all the air out of a giant chamber. But it's a very terrible video because it was taken in like the 60s with terrible equipment while on the moon. So it's all grainy and suspicious looking. So this one's much nicer, and it's just crazy they had like so many people just to do this. Like both times we've done that experiment, one we had to make a rocket and go to the moon, and then we had to like pump all of the air out of like the world's largest vacuum chamber. So it's hard on Earth to get no air resistance, which is good because we like breathing. So that's the takeaway here. Just some summary here, some details, sort of my frequently asked question sheet about G, which is G is always positive. Acceleration in the y direction when we're talking about gravity is negative G, meaning that you have to put the negative in yourself. G is not gravity, it's the acceleration due to gravity because G is going to be different on the moon. It's also going to be different like at the top of Everest by a very small amount. This only is true on Earth and only parts of Earth, so like under the water, up high, not true. And then when we talk about acceleration in units of G, it's just multiples of 9.8 meters per second squared. So if you have 2g, that's 2 times 9.8 meters per second squared, okay? Okay, 3g is 3 times 9.8 meters per second squared, and so on and so forth. So when people talk about experiencing g's, that's what they mean, right? Because humans are designed to experience 1g, so once you start giving us more or less g's, things change. Okay, so we're going to do an example here for Freefall, and we're going to go through it slowly with the process we used, because this is very much a type of problem that might be on an exam or in a homework, and so I want to get you the idea of how to actually go through the process of these. So the first thing we do is we read the question and we figure out what we know and don't know. So, oops, I'm going to start by picking a color. So we have a rock released from rest. That means velocity is 0. At the top of a 100-meter tall building, that's going to be a y height. And we want to know how long. So that's a time. Does it take for the rock to fall to the ground? So we're going to say that's a height of 0. And what is its impact velocity? So that's going to be velocity final. So we know that a rock is released from rest, means that our initial velocity is going to be equal to 0 meters per second. We know that our initial position is going to be 100 meters. We don't know what our final velocity is, but we're going to need to find it, because that's what this is. This is the impact velocity. And we know that our final position is the ground, so we'll call that y1. Actually, let's call v final v1 instead of v final. Because remember, like in other problems, we may not have just 2 points. We could have more than 2. We could have 1, 2, 3, 4. That lots of subnotations, but we know that v1 and y1 happen at the same point, and then the ground is at 0 meters, and we're also looking for the time interval, which is this. So there are 2 questions to answer. What is its impact velocity? And how long does it take to fall to the ground? Okay, so these are our knowns and unknowns, and we want to next draw a picture. Okay, so in order to draw a picture, we're going to start, this is going in the y direction, so we'll draw a y-axis. Okay, so this is y in meters. We know that this is going to start at the top of a building, so we'll call that 100 meters. And it's going to end at 0. So this is 0 meters. So if we draw our little rock, let's say this is our rock, and I'll color it in. So, rock. Okay. At this point, we have y0, velocity 0, which is 0, and time 0. Okay. What we know is going to happen is we know, because this is a free fall problem, that the acceleration the whole time is the acceleration due to gravity. So that means A is equal to negative g. Okay. We also know that because there's acceleration, we're going to start with, sort of small arrows. So 0, then it gets bigger, and then it gets bigger, then it gets bigger. And at some later time, this rock ends up down here. There should be a really large velocity down here, but at this later time, we end up with y1, v1, and t1. So those are our points for the rock when it's at this position. okay? So as far as our knowns and unknowns go, I'm gonna highlight, so the things we need to know are the times and velocity 1, right? Because that's impact velocity, and the time is the change in t, okay? And then velocity 1 is our final velocity. Okay, so the first thing we want to do is make a prediction so that we know if we have a reasonable assumption. And so as far as time to get to the ground, if you're dropping something off a 100-meter tall building, it's not going to take a long time. Like, it's not going to be 10 minutes to get to the ground, so we'll probably think maybe definitely less than a minute, probably only a few seconds, okay? So our estimate for answer is less than 1 minute, probably 1 to 10 seconds, just based on, knowing what things are like when they fall off cliffs. And then for our impact velocity, that's probably going to be going pretty fast, but like, the speed of a car maybe. So like something like 10 to 100 miles per hour, which would be something like 5 to 50 meters per second. That's just the estimate range. So for our two different things we're looking for, those are our estimates. All right, so we have our knowns and unknowns, and we have our drawing. So what we'll do next is we'll figure out what equation we need to use. And we want to know how long is it going to take the rock to fall to the ground. So we're going to need one of the kinematics equations. We see that we have position, so we probably want this position equation. And I'll call this y final is equal to y initial plus v initial delta t plus 1/2 a delta t squared. But because we actually know some of these things, we can plug them in. So what is y initial? Well, we know y initial, we'll highlight this in blue. Y initial is this, right? Y final is this. We know our initial velocity, that's going to be 0, because we know it's that. We're looking for delta t, but we also know that our acceleration is going to be g. So we'll plug this stuff in. That's going to be 0 is, this is 100. This whole thing goes to 0. So this is minus, because we have minus g instead of a, 1/2 g delta t squared. Okay, and we can plug this in later, but I'm just plugging it in now for the heck of it. So we end up with, we can rearrange this algebraically. We get 1/2 g delta t squared is equal to 100 meters. Okay, and we're going to solve this for delta t. So delta t is equal to 2 times 100 meters divided by g, and then we're going to take a square root of this. Okay, then we can plug in the rest of our numbers. So that's going to be the square root of 2 times 100 meters divided by 9.8 meters per second squared. Now remember, you don't need to add the negative sign here, remember, because we already put it here. So make sure you don't plug in the negative sign multiple times. When we actually solve this, because this is a square root, we end up with plus and minus 4.52 seconds. Of course, negative time because this is a real world problem, doesn't make sense. So we choose the answer that makes the most sense. That's 4.52 seconds. That's our delta t. If we look at that, that looks pretty good, because what did we say our delta t likely was? Well, we said it's probably less than a minute, probably 1 to 10 seconds. Basically, if you're dropping something off like a 300-foot or 100-meter building, that's like a 30-story building, that would be somewhere between 1 and 10 seconds. So we guessed that our time would be somewhere between 1 and 10 seconds, and look, it is. Okay? Cool. For the second part of this problem, we want to figure out the impact velocity. Because we already know the time, we can use either of the other kinematics equations, but the one that's probably most useful to find the final velocity is the one that has final velocity in it, because remember, you can either have, well, there's two that we could use, right? We could either use, and either of them will work fine. We can either use V final is equal to V initial plus a delta t, or we can use V final squared is equal to V initial squared plus a, plus 2a delta y. Either of these should work, but it's probably easier to use the one without squares, so we'll end up using this one. I'm going to bring that down a smidge. Remember, once again, we know that our V initial is going to be 0, just because we have that over here. So we have V final, and this is actually going to be relatively straightforward. So our V final, oops, oh my gosh, is equal to, remember, A is negative G, so negative 9.8 meters per second squared, and delta T is 4.52 seconds. So we plug those in. That gives us a V final of negative 44.3 meters per second. So that's our V final, which we'd call V1 in this case. And let me fix that over here. V1. So as we recall, when we made our prediction, we decided that this would be between 1 and 100 miles per hour, so 5 to 50 meters per second. Because remember, if you want to go from meters per second to miles per hour, you can roughly, very roughly, just double the number. That it gives us an approximate miles per hour. So yeah, this would be about 90 miles per hour. Why is it negative? Well, remember, velocity is a vector, so that means this is pointing down towards the ground because that's the direction it's falling. And hopefully that makes some sense. And that is our second answer, our impact velocity. Okay? So yeah, these answers make sense with how we estimated. Remember, the sign in this case matters, right? The sign is negative because you see at this point the velocity would be really big and pointing down. Okay? These arrows are not to scale, but yeah, we're going to have something negative. Okay, we'll start out just reviewing what freefall is. This is a clicker question, so take a minute and give people time to wander back in. Okay, we're not 100% sure. Please discuss and vote again. All right, so the answer is going to be E. It's always constant because remember, in free fall, what is the acceleration? Negative 9.8, so 9.8 down. Okay, what's going up when you throw it up? The position vector, the velocity vector, all of those are up. and then they change, but the acceleration always down, okay? So because our velocity vector is up and our acceleration vector is down, that's why it slows down, then it stops, then they're both down, so it starts to speed up, okay? So don't confuse velocity and acceleration. Let's try a second one. Okay, it's a nice little slope there. Please discuss and we'll vote again. Better. Yeah, so remember, acceleration always down, but since you throw the ball up in the air, it's going to decelerate, right? Because it's really about the direction. So it's going to have a velocity that slows down, right? And then it's going to speed up on the way back down. Perfect. Okay. So here's a problem you should try doing on your own. It's similar to the previous example we did. It's got sort of the same idea. Where once again, the only real complication that's different is we're splitting this one into two parts. So I'll give you a few minutes to sort of do this on your own, and then we'll go over it. So pause here and take a shot at it. It's very important when you're doing these problems to sort of try to set it up yourself, even if you can't solve it, before you go through the solutions so that you can understand sort of where I'm coming from. It's always easy to look through a solution and have it make sense, but then if you can't do it yourself, it's kind of pointless. So we're going to set this problem up the same way we set up the previous problem. So we'll start by sort of just going through the problem and finding the information. So the first part is just sort of informational. We're learning about Springboks. So the Springboks is an African antelope. It gets its name from its magical jumping ability. Not really magical, but you know. So whenever it's startled, it'll leap straight up in the air. This is called a pronk, which is just a great word. And then the Springbok has to go into a crouch to perform a pronk. So basically, it crouches down, then it extends its legs forcefully. It has an acceleration over 0.7 meters. Now that's like basically as it goes from crouching to standing up. And then its legs fully extended, it leaves the ground and rises into the air. And we want to know how high it goes. So here's our main things. We know that it's going to go 35 meters per second for about 0.7 meters. That's phase one. And then legs fully extended, it leaves the ground, right? So this is 0 and rises into the air, and we want to know how high it goes. Okay, so the question we're answering is how high does it go? But what does that actually mean? Well, the way that we write that in symbols, that's probably going to be delta y. But in order to understand that, we're really going to need to draw a picture. So let's start by drawing our picture. So essentially, we're going to take sort of the center of the Springbok to be its whole thing, because what it's doing is it's like to draw like a weird set of pictures about it. So let's say this is our Springbok. So it's going to start crouched down, and then it's going to end like this. This is the first part. Actually, let me draw that better. Okay, and actually let's move this over. So it starts down here. Oops. And then once it does that, it's going to rise into the air. Okay, so there's 3 parts, but we're going to sort of break this up, so I'm going to expand this out a little bit. So here's the top of its trajectory. All right, here's when it's, I'm going to duplicate this one because it's cuter. So here's the top of its trajectory up here. And here's where it starts. So it's going from here to here. It's really going from here to here, but I'm going to just spread it out so it's easier to graph, okay? And then we'll draw our actual y-axis. So this is our y-axis. So this would be, so remember, we're just going to sort of use the middle of it. So we're going to call this position 0. Because this is the position we're measuring from here to here. We could measure from toe to toe. That might actually be easier. No, we're going to go from the middle because that'll make sense. Just give it a second. So we're going to call this position 0. This is going to be, we'll call this y max. And this is what we're looking for, kind of, not to. Okay, this is similar to this because remember we're really just looking for delta y is this distance, but because we're drawing this on a number line and this is 0, delta y is going to be the same as y max because it's y max minus 0. This distance here, this is basically this is going to be 0.7 meters, right? Because we're going from the middle here as it stretches up. Okay, so really this is the standing up distance. All right. During this time period, we have an acceleration. We'll call acceleration 0. Which is 35 meters per second squared. All right. And once we get up here, we have an acceleration. Now this is a bigger acceleration. We have an and this one's constant too, but here we have an acceleration a1, which we'll call negative g, which is 9.8 meters per second squared down. Okay. So essentially, if you look at the velocity, we're going from a 0 velocity to a small velocity to a much bigger velocity because it's accelerating quickly. And then as we're going up, we're going from a big velocity to smaller velocities. So we start off with a big velocity and then it starts getting smaller and smaller and smaller until it stops. Okay? So here we're speeding up, here we're slowing down. And if we want to, now we've figured out, here's our acceleration, right? That's this. Oops. And then here's our distance. That's this. And then leaves the ground and rises into the air. That's our 0 point. So we're going to call that this. And we want to know how high it actually goes. So that's what we're looking for. Okay. In order to, there's one more implied thing we have to figure out, and that is the velocity. Let's call this y max y1. We'll call this point, let's say this is 0. We'll call it y2. So we'll call this y1. We'll call this y0. We'll call this y2. Okay? Delta y is going to be equal to y2 minus y1. But remember, y1 is 0, so delta y will be equal to y2. All right? This would be v2, and this will be v1, and this will be v0, which is 0 meters per second. We don't know velocity 1, but we do know that velocity 2, now this is an implied thing because we know it's the height is going to be the maximum height, so that's going to be the turning point because it can't go any higher than that without turning around. That means this has to be 0 meters per second, okay? that's because we know this is a parabolic arc that this thing is making in the y direction. And if you remember calculus, if you want to find the maximum, you take, if this is the position graph, you take the derivative. That means our velocity is 0. So just from knowing in calculus that taking a derivative should give you 0, that means our velocity has to be 0. But we also know intuitively when this thing's at the top of its peak, at the top of its arc, at the top of its jump, its velocity should be 0. So that's an implied value. Okay, so we don't have any time here. A couple things. How high do you think it's reasonable for this thing to go? So let's estimate. Well, it's probably not going to go like 100 meters in the air. Like if you could jump, you could probably jump 1 meter. Maybe this thing can jump anywhere between 1 to 10 meters. 10 meters even seems pretty extreme, but just to give us a range, an order of magnitude estimate, let's say 1 to 10 meters would be reasonable. Okay, now going to the equation we would want to use, we probably want to use the kinematics equation because remember, these are all constant acceleration. We probably want to use the one that doesn't have time. Okay, we're going to need to know velocities and displacements. We have one equation, v final squared is equal to v initial squared plus 2a delta x. In this case, we'll call it delta y just because we know this is in the y direction. This equation is probably going to be super useful for both parts, both phases, right? So to start out with, we'll do just this part, and we'll find v1 in order to figure out what our starting velocity is for this jump, because we know what the acceleration is. So in order to use any kind of position equation, like we're probably going to want to solve for delta y later, right? We start in the beginning phase, we'll call this phase 1, and then this would be phase 2. So this thing jumping is phase 1, this thing flying through the air is phase 2. So in phase 1 we know we're just getting force from the legs of this guy, and we know the displacement, so we're going to need to figure out the initial velocity. So, our final velocity, and use that as the initial velocity in the next phase. So we start out in phase 1 with this equation. So let me move this over. Oh no. Oh, I've totally screwed that up. Hang on. Okay. So phase 1. That means v1 squared is equal to v initial squared, but remember, our v initial here is 0. So that becomes 2. Our acceleration is 0 delta y. Okay, but these are the things we know, so we're going to find v1 is going to be equal to the square root of 2a0 delta y. In this case, this is going to be 2 times 35 meters per second squared, and delta y is 0.7 meters. Okay, so these are all values from phase 1. So just to be clear, this is our 0.7 meters, and this is our 35 meters per second. This is all phase 1. We plug all this stuff in, and that gives us v1 is equal to, 7.0 meters per second. We didn't have an estimate for this, but we're plugging it into the next part. Now that we know our velocity that we start with, we can use the same equation, but now we're going to use it to say v2 squared is equal to v1 squared. This is now our initial velocity for the next phase, phase 2. Plus 2a1 delta y, which is a different delta y. We're now doing the delta y that we're looking for, we're the answer that we care about. So it's going to be this delta y. Remember, so the same as y2. All right, so We know what V2 final is. That's going to be 0. So then we get 0 is equal to V1 squared, which we know, minus 2g. Remember, we plugged in negative g for A1, delta y. In this case, we want to solve for delta y, so we're going to do some algebra before we plug in numbers. V1 squared is equal to 2g delta y. That means delta y is equal to V1 squared over 2g. Okay, I've sort of run out of space, but I'll bring this up here. So delta y is equal to V1, remember that's 7 meters per second squared over 2 times 9.8 meters per second squared. You plug all this in, and this should give us 2.5 meters. So our final answer that we're looking for is going to be 2.5 meters. Now if we go back to our estimate, we had estimated it between 1 and 10 meters, and this definitely qualifies us. 2.5 meters is actually pretty high. I mean, a meter is 3 feet, so this is going to be like, this can jump over a person essentially. But that does seem reasonable for an antelope, so we're in pretty good shape. Just to review, what we did here was we looked at this as 2 phases. We knew for the part where this guy is taken off, this Springbok is pronking, that it has this really rapid acceleration that's constant from 0 to 0.7 meters. That gives us our initial speed. We solved for our initial speed here. Then we use that to plug in our initial speed here. It ends up over here, and so that we can get our final velocity of 0, right? Remember, we know there's an implied final velocity of 0 because this is the peak of the jump, and then we use that to solve for the final position. And we used both times this equation, the kinematics equation that does not include time, because as we noticed, there's no time given in the problem. And the other thing, this how high, we know included sort of the implication that we have to get to the peak, which is the max height at a velocity equals 0, because that's a turning point in our arc. Okay.